I'm Jake O'Neill, creator of Animagraphs, and this is how nuclear power works. For our demonstration model, I've chosen a design that shares much of its DNA with historic reactors, but combined with updated safety systems based on our learning from failures through the years, and an overall goal to make a simpler reactor. This is the Westinghouse AP1000 design. The reactor core is situated just below ground level, with 157 individual nuclear fuel assemblies in the core. Each with 264 fuel rods apiece. Our fuel, enriched uranium pellets, is stacked end to end inside of these completely sealed, welded rods. There are about 430 pellets in a rod. So in all, that's around 16 million little uranium pieces in the entire reactor core. We'll get into exactly how the fuel works in a bit. The nuclear reaction in the core generates heat. And that heat is used to make steam. There are two steam generators at either side of the reactor that take in super hot water from the reactor core. And use it to boil a completely separate water feed. Keeping these systems separate is crucial, as we'll see. The resulting steam passes to the turbine building to spin high and low pressure turbines, with the generator at the end of the combined shaft for making electricity. Our plant can power nearly 1 million US homes as a general figure. The steam, having done its work, is cooled, condensing it back into water so it can run through the loop again. There's a cement pad of cylinders somewhere on the reactor lot for spent fuel rods in their permanent storage containers. Existing AP1000 installations over the world are often built in pairs, so two reactors would produce about 120 to 150 casks over the designed 60-year lifespan. I don't know why, but before researching this project, I never really understood what radioactive waste actually looks like. There are other kinds of waste produced, but this is the main nuclear fuel waste we hear so much about. 60 years of power for an entire city sitting right here on this pad. Now let's look at how each system works in detail. We'll head down to our new, unused fuel as it arrives at the power plant. A semi-truck carries two new fuel containers. Each container has two fuel assemblies inside. The containers are lifted off the truck by an overhead crane, thoroughly inspected, and moved to a covered dry storage pit. The fuel assemblies aren't meaningfully active yet, and so can be handled and stored in this simpler way before entering the core. Of course, this area is a sterile, high security zone, as fuel assemblies must be generally protected from damage and contaminants, even though sealed in metal tubes. Assemblies headed for the core are moved from dry storage into the spent fuel pool. the new fuel elevator lowers them down. So they can be handled by the fuel handling machine, which is another crane with its own array of special tools and attachments for each dedicated task. This is just the beginning. When handling a sensitive assembly worth a couple $1 million a piece, where mistakes aren't really an option, every step must be planned out in advance. New fuel will be transferred from this pool through the refueling canal and cavity and placed into the reactor during the refueling process. Let's skip over to the reactor now and see how fuel works when it's fully loaded and operational, and then we'll see the refuel process and more. We return to the uranium pellets inside a fuel rod as shown earlier. This is uranium-235, which generally means the atoms that make up this pellet each have 92 protons and 143 neutrons in the nucleus. It's altered or enriched from naturally abundant uranium-238. I'm showing little spheres here since it's what we're used to, but in reality, these subatomic particles are more like a field or cloud of probabilities, not little glass marbles. What my model really says is, this is how these subatomic particles reliably behave in these conditions. All the forces acting here get pretty complex, so I'm just going to state some things play by play to simplify it while keeping it accurate. For example, there are forces that cause these individual bits to repel each other, but other forces that stick them together to make the nucleus. So there's a tension of opposing forces at play here. With this altered, uneven neutron count, the nucleus is actually at a sort of unstable, higher energy level. If a free-floating neutron comes along and bumps into this nucleus, it will be attracted into the system and pair up in a way with that extra available neutron, causing the nucleus overall to settle into a more balanced, lower energy state. But the energy released by this pairing stays in the system and actually has the effect of deforming the entire nucleus. The main force gluing these parts together, the strong nuclear force as it's called, only works at very short distances. Once these particles are pushed far enough apart, they forcefully repel each other instead, causing the uranium atom to fragment into entirely different elements. If you weigh these elements on an atomic scale after this split, the parts actually weigh less in total than the original uranium atom. So, some mass gets converted directly into energy, in our case generating immense heat, but I don't pretend to understand things beyond that reality. The fracturing or fission process is based on probability, and though hundreds of fission products happen in the core, the most likely resulting elements are things like strontium, krypton, and barium or celsium because their proton and neutron balance results in the most stable nucleus. And because nature prefers those stable elements, free unused neutrons reliably get released that don't find a place, as it were, in the resulting products, at an average rate of about 2 to 3 neutrons per fission event over the whole core. Those free neutrons now travel through the reactor core water until they interact with more uranium atoms, causing more fission events. By the way, there are a multitude of energies, particles, waves, and whatnot released at the fission event. And the resulting byproducts, which are just individual elements or atoms, might keep releasing their own stuff afterward, trying to balance themselves out. This is radiation. The fission byproduct strontium, for example, looks like calcium to organic life forms, and when it gets integrated into living structures, but keeps shedding particles, energy, and so on, That's what causes radiation damage. Continuing on, if we zoom out a little more and show uranium-235 atoms as red circles in their atomic crystalline structure, again, more of a visual metaphor, once neutrons start flying about, eventually all usable fuel is cracked into other elements and the pellet is spent. In reality, the usable portion is only about 5% of the overall pellet, so it doesn't turn to dust or anything like that. It's just not good for nuclear fission anymore. Keeping with fission visuals, I've scaled up our free-flying neutrons massively so they're visible to the naked eye inside of the reactor core. Of course, the actual count would be some ridiculous number. Though fuel pellets are sealed in, the containing rod or cladding is made of metal, a zirconium alloy that has low neutron absorption capabilities, allowing free neutrons to easily pass through this casing. In contrast, the reactor vessel is made of 8 inches thick steel for a very high probability of neutron capture. The whole core, with all its 16 million pellets, takes about 18 to 24 months to work through all available fuel before needing to be refueled with fresh uranium. The core requires a highly tuned environment to make this intricate fission dance possible. If free neutrons zing too quickly through the core, for example, that can actually prevent fission events from happening. The water circulating through the core contains boric acid. Boron is a great neutron absorber, so varying the concentration of boron in the water has the desirable effect of slowing neutrons so uranium atoms can reliably absorb them. There's also a robust system of control rods. And drives to insert these rods into the core and control the reaction that way. Fuel assemblies have empty spaces so control rods can be lowered in between. Control rods are made of metals that literally absorb neutrons to mute or stop the core reaction. They come in a few key types. Black rods, for example, are powerful neutron absorbers made of a silver alloy with stainless steel exterior. They're called black rods for their properties, but I'm also going to color them black for easier viewing. Gray rods complement these, but have more stainless and less silver for weaker neutron absorption overall, so they're better for fine tuning. These two rod groups move in small increments and not necessarily all that fast. There are shutdown rods, which I've highlighted in red. These have a similar material composition to black rods, but they're designed to be either up or all the way down. If an emergency happens, they'll automatically fall into the core in about 2.5 seconds to shut things down entirely. There's a final type of gray rod, but I'll highlight it in white, which can sort of push the energy ball in the core around in space. Because the pellets are a grid, the core actually acts like a 3D ball of energy. And these special axial control rods keep that power ball aligned in 3D space. All these components are designed to wear and be replaced as they absorb neutrons over time. The control rods are held by a bracket called the spider. With a main rod that extends up into the drive mechanism. The core is an extreme environment, and these rod assemblies must live in that environment. So, there's some nifty engineering here that keeps rods sealed from the components that drive them. The control rod has ridges where latches can engage. Outside of this sealed inner compartment, there's a thick copper coil. And as you may know, when you run electricity through copper wiring, a magnetic field develops around it. The resulting electromagnet, as it's called, can lift the bracket or armature through sealed compartment walls. Which engages the latches. If power is lost, a spring in the system will naturally push latches open. Releasing the rod by default. These lower latches can only hold the rod in place. There's a set of armature rings above to move it. The middle armature and latch set grips the rod. While the top electromagnet lifts the entire chain of parts. By alternating which electromagnets engage and when, you can move the rod up or down, or just hold it in place. Now you've seen how we get the nuclear reaction going and how we control it. Remember, the main goal is to heat up water as it moves through the reactor. Water comes in at the midsection through a large pipe called the cold leg. It flows through a separate chamber outside of the core to the bottom of the reactor vessel. There's a flow skirt here with holes to maintain equal flow as it enters the core. There's a vortex suppression plate here as well to keep water from spinning in the bowl at the bottom. The overall system moves about 300,000 gallons of water per minute, or half an Olympic swimming pool. This tremendous flow rate must be tuned at every transition. There are supports here to brace the core, not only for its own weight, but also for that much water force flowing through. Another plate has metal pins to align and secure fuel assemblies. Each individual fuel assembly has a nozzle at the bottom, which is highly engineered with complex passageways to channel water flow as it enters the assembly and also trap any possible debris that could damage fuel cladding if it catches and vibrates against fuel rods. There's another nozzle as we reach the top, with springs that press against a removable core plate to anchor everything down. Water flows through the forest of tubes, picking up about 73 degrees of heat, going from 537 degrees at entry to 610 degrees at the top, which happens in about 1 second. We'll shortly see how we keep water at such high temperatures without boiling. The water flows out of the core assembly into piping called hot legs at either side. you can see a dense network of support tubes for the control rod machinery above. The nest of control rod drives has its own cooling ducts and fans. The whole thing is part of a unified module that lifts off as one piece for easier disassembly and refueling. Now let's follow our heated water outside of the reactor. Connected to one of the hot legs, there's the pressurizer tank. This is how we keep core water from boiling even though it's way above normal boiling temperatures. This tank pressurizes the system, and the boiling point of water under pressure changes with pressure levels. The tank itself is a simple enough design, with a bunch of heating elements at the bottom that boil water, making steam. And since water expands 1,600 times when it becomes steam, this exerts pressure on the connected system. To let off some pressure, there are cold water spray nozzles at the top to cool steam back into water. Boiling water would change its properties, making it a less effective moderator to slow down neutrons in our pressurized water reactor, or PWR type design. Also, our design prefers a solid coat of water around fuel rods for best heat transfer, where bubbles or steam would conduct heat poorly. The hot leg piping carries heated reactor water to the steam generator. It rushes in at the bottom and through a flow plate, guiding it through a massive bundle of 10,000 plus half-inch diameter U-shaped tubes at about 80-foot length on average. The reactor water carries radioactive elements that we need to keep sealed and contained from other systems at all times. So, a completely separate water feed is used to generate steam. This separate feed is actually water returning from the steam turbines and electricity generating gear. It's pumped through a feed water ring about 2/3 the way up the steam generator tower. This ring has curved spouts called J-tubes, so water must always be pumped in instead of simply falling or draining out on its own and allowing steam into the feed system, which we don't want. Water descends down the steam generator walls and into the heating chamber. The U-tubes give ample contact area for heat exchange. They must remain covered with water at all times for even, reliable heat transfer, and to protect heating pipes since they're not designed to run dry without water surrounding them. The water column comes to a boil, producing steam at the top. For best steam performance, we want the cleanest steam gas possible with very little water content. Water drops in our steam become like rocks, hitting sensitive turbine parts downstream. So, there are multiple water removal stages as steam expands upwards. The first stage is a pipe with a spiral plate called a swirl vane. The forceful swirling action ejects water droplets to the outer casing. Where the steam flow pushes drops up and through a screened gap at the top. Water then flows down an outer sleeve to join incoming feed water for another go-around. Our cleaned steam continues upwards to the second water removal stage, with banks of zigzagged plates, where heavier water droplets will smack into these angled surfaces and drain downwards, while dry steam flows through and up. Our purified steam gas exits the steam generators at either side on its way to the turbines. Down at the bottom of the steam generator, we rejoin our reactor water loop. Remember, this is core water that never becomes steam or mixes with that separate feed. It flows through the U-shaped tubes back down the other side of the separator plate, then out of the steam generator. Here we see two reactor coolant pumps. The water is called coolant in nuclear terms since it cools or removes heat from the reactor. These pumps are part of our modernized design. They're completely sealed as a unit, from the finned wheel or impeller that moves water to the electrical motor which drives the impeller. Motors in older designs were outside of the sealed pump section, and the drive shaft seals were a source of radioactive coolant leaks. The fully sealed combined unit is a canned pump. You'll remember that we're moving 300,000 gallons a minute over 4 of these pumps in total, so they see heavy, constant work. The pumps have to be reliable because, though there are many safeguards and allowances in the system, if things don't flow as they should, that's how you get dangerous heat buildup and catastrophic failures. If you're not extracting and moving heat through the system, there's easily enough heat in the nuclear fuel to start melting metal parts. The pumps send water through the cold leg back to the reactor, and the cycle continues. Our setup can be classified as a 2-loop reactor, since there are 2 steam generator loops. The reactor and steam generator system are surrounded by the most robust shielding. The fuel in the bottom part of a reactor sits just below ground level. Support structures and walls are made from steel panels that also serve as forms for pouring concrete. Each major component has its own protective shell. The whole installation sits in a concrete-filled bowl formed by the lower portion of the containment vessel. The containment vessel is a 1 3/4 inch thick continuous steel chamber with domed top and bottom shapes for ultimate strength. At the top, there's a utility crane called a puller crane since it operates in a circle. Also here at the top, we start to notice the shield building itself, which holds the containment vessel. 3-foot thick concrete walls enclose and protect the installation. The building is part of the passive safety system, meaning a system that works to contain disaster without needing electricity or human intervention for a sufficient period of time. So let's see what happens as the plant experiences emergency conditions. The 4 main systems we've just seen, the reactor, Pressurizer, coolant pumps, and steam generator all have sensors to detect abnormal conditions. If 2 of the 4 report a serious problem, that's enough voting power to trigger emergency response. So naturally, this also applies to the worst case scenario: loss of off-site power or total blackout, and failure to start internal diesel backup generators. Internal systems signal the alarm and main electrical breakers trip, disconnecting power to valves and devices that default to an open state. For example, within moments, control rod latches naturally swing open as we saw before, allowing the control rods to fall into the core. As we're stopping the reaction in the core, we need to start cooling things down right away, since again, the core runs hot enough to melt itself if that heat isn't being used and carried away. A set of spring-loaded valves snap open on loss of power, connecting a heat exchanger to the reactor plumbing. The hot, pressurized reactor water naturally rushes into the colder heat exchange tubes, which sit submerged in a nearby refueling water tank that we'll check out in a bit. The exchanger lets heat radiate out of reactor water into the pool while keeping it separate. Coolant drains by gravity back into the reactor, and the cycle repeats as long as reactor water is still hotter than the pool's ambient temperature. After a few hours of this, the pool will start to boil, letting off steam into the containment vessel. Reactor coolant pumps have a flywheel, so the impeller keeps spinning for a time without power. However, if we're leaking coolant water somehow, there are core makeup tanks with fail-open valves. Hot reactor water or steam can enter the tank to help push makeup water that otherwise gravity drains into the core to offset losses. If water losses outpace this gravity-fed makeup loop, there are pre-pressurized tanks below those for a rapid, forceful water injection into the reactor. To drop system pressure, plumbing from the pressurizer allows steam to vent into that same refueling pool, condensing the steam into water and gradually depressurizing the system. At more advanced emergency stages, coolant is concentrated in the core, and the hot legs are now full of steam instead of water. Valves here can vent this steam directly from the hot legs into the containment vessel. Also, at later emergency stages, the whole refueling pool can drain by gravity into the core if needed to maintain cooling. Now we can look at how the shield building itself factors into this passive process. If superhot steam is filling the containment vessel from various sources, we need to cool the whole vessel while keeping everything safely contained inside. The hot interior temperature difference will naturally draw in cold outside air through vents, with holes that are angled to protect from external threats. Metal baffles guide air down and around where it contacts the hot containment vessel exterior. The air flows back up, carrying heat away from vessel walls and out through a protected vent structure at the top. To greatly enhance cooling effect, there's a large permanent water tank here that holds 800,000 plus gallons of water. It drains by gravity to a distribution bucket, which sprays water evenly onto the vessel. The water absorbs heat and evaporates into the ventilation airstream. This tank is designed to work passively for 72 hours, or 3 full days, before water must be pumped in to refill it. These passive systems work automatically and without power to both cool the reactor down and depressurize it, while containing radioactive materials. Some of the most famous disasters were worst-case scenarios where off-site power and on-site backup power all go out at once. Now that we've seen how the installation supports and contains the nuclear reaction, let's zoom back in and see how refueling works, since that's yet another area where we have to deal directly with radioactive material. Every 18 to 24 months, about 1/3 to 1/2 of the core fuel gets replaced with new fuel. Having 2 reactor plants is handy to run one while the other is offline. The reactor is shut down and cooled off. The polar crane attaches to and lifts the entire vessel head as a unit, which includes control rod drives, all the way down to the actual thick steel reactor cap. Water from the nearby refueling tank floods this cavity to act as a radiation shield. The vessel head is kept just above the water level. And once the pool is full, the assembly is placed on its special storage pedestal. The control rod drive components are also lifted out. The core is now exposed beneath a layer of shield water. We're ready for refueling. A separate refueling machine or crane lifts spent fuel out of the vessel while always keeping it at least 8.75 feet below the water surface. These moves are done by remote automation, but are carefully observed by plant operators. The spent fuel unit is placed on an upending rack that tips it horizontal, so it can pass through the otherwise sealed refueling canal. The canal goes through the containment vessel wall as well. Spent fuel is upended again at the other side, and another machine lifts it into a submerged storage grid. This is the spent fuel pool. It's 42.5 feet deep, so fuel always remains underwater even when being moved. It can hold 612 fuel assemblies. The water has boron, like the reactor, to stop neutron flow. New fuel comes in through this same pool and does the same sequence of moves to pass through the canal and load into the core. The reactor is reassembled and restarted. The whole process takes about 15 to 25 days. To get the reaction going again, some fuel rods are made of elements like californium, which naturally emit a lot of neutrons. In dry storage, these neutrons travel too fast for fission events. It's the reactor water, acting as a moderator, that slows neutrons down, but not too much, giving time for fission to happen. Back at the spent fuel pool, we return to our used assembly. Day 1, it's hot enough to make the pool boil if pumps weren't actively cooling the pit. After year 1, it's about 90% cooled. And after 5 years in this pool, it's cool enough to enter permanent waste storage. It's transferred underwater through a gate to an awaiting dry storage cask. With an inner metal canister that holds spent fuel. Surrounded by thick concrete and additional metal layers. It's transferred to a dry pit for washdown. The inner canister has all air pumped out and is pressurized with helium for better heat conducting and rust avoiding properties. It's welded shut. The container design allows airflow around that inner canister so fuel can passively cool in permanent storage. The cask is lifted up and placed on another truck to be transferred to the outdoor storage pad, where it can then be moved by a special tracked vehicle that manages cask storage. I'm showing the full 60 years of radioactive fuel waste here, which represents the designed life cycle of our plant. With 2 plants in operation, that equals about 120 to 150 casks total. The casks securely contain all this stuff, but for reference, dangerous byproducts that could give a lethal radiation dose outside of the metal fuel rods decay in seconds to months. The fuel within takes another 100 to 500 years to cool down to normal temperatures. And direct contact with the spent uranium will not be safe for 500 to 10,000 plus years. And so far, no nuclear country has a permanent solution built. Planned, yes, but not built. The idea is to put casks far underground in solid excavated rock chambers. Even that seems odd, but we already bury all our trash, so then again, maybe it's not so odd. Returning to our reactor, let's finish the cycle and see how our plant generates electricity. We're turning 300,000 gallons of water per minute into hot, dry steam. That steam travels out of the steam generator and out of the containment vessel through a room with isolation valves to keep these systems separate and blow off excess steam pressure if needed. It passes through the high-pressure turbine first. The hot steam expands into the chamber, pushing and spinning turbine wheels with many blades. And since the steam cools some as it performs work, moisture starts to form. It's actually efficient to have a stage here to remove that new moisture and reheat the steam a bit before it enters our low-pressure turbines. The large low-pressure turbines absorb the remaining useful steam energy. All of these turbines are on a long connected shaft that spins an electric generator at the end. It's most efficient to recycle the steam over and over, so everything between here and returning back to the reactor building is meant to clean up our steam and turn it back into water. Steam flows out of turbines into condensers. There's a separate cold water supply that flows through many tubes. The steam passes by these tubes, condensing back into water droplets as it cools. The resulting water pools at the bottom of the condenser chamber. The separate cooling water supply in these tubes often comes from a nearby natural water source, like the ocean, or those instantly recognizable cooling towers if the installation uses air to cool the water loop. Water vapor from those towers bleeds off heat. It's not smoke. From the condenser, our feed water, now at its lowest pressure, gets cleaned in a water polishing tank since it picks up impurities on its dramatic journey. Then it gets heated back up in various low-pressure tanks that cleverly take heat from the condenser chamber. From there, it flows to a de-aerator tank on this upper level to remove air bubbles. With a long vertical pipe, so gravity will ensure no bubbles remain. Main feed water pumps pump and pressurize the stream for a final round of high pressure heaters. Now our feed water is clean, free of air bubbles, and heated so it won't cause a thermal shock to the steam generators, which need the incoming water supply to be at about 440 degrees Fahrenheit. Feed water passes another set of valves before entering the containment vessel, and the cycle repeats. As a truly amazing side note, this is pretty much exactly how old steamships work, as you can see if you watch my recent video on the subject. I see the draw of nuclear power. These relatively tiny plants produce incredible output at comparatively tiny waste in return, but as we know, all of that potential comes with risk. Either way, knowing how nuclear power works is really cool.